test, and synchronization. So, you all heard Rob talk, and Iceberg called it a short-term journal, right, where it enables us to go back in time in a very granular manner. That's pretty much how we do it. You configure in Zerto the amount of time you want the journal to take, not the space, right? That's very important. The space is a hard limit. You configure the SLA. I want 24 hours. I want 7 days. I want 2 weeks. And Zerto will grow and shrink the journal to accommodate your needs. And we're going to explain how all of that works. So let's start with the basics. What do we have? Inside, single VM, single host, right? We have that works. We have a source VM. The source VM has a number of virtual disks. We have a VRA, the virtual replication appliance. We have one of those per host. That means there is, for any VM, there is a virtual replication appliance on that same host as that protected VM. Now, data gets captured, gets to that VRA. The VRA compresses the data, sends it over to a target VRA. Target VRA can reside on the same site, can reside on a different site, more likely on a different site. We have our journal, okay? The journal is actually comprised of a number of virtual disks. The disks are not disk per source disk, but it's a number. It's actually a dynamic number of virtual disks. I'll explain exactly how that number is determined. But there is one sort of journal entity per source VM. And then we have what we refer to as the recovery disks. And those are created when the VPG is being created. And that would be a one-to-one mapping. These are the disks. There's a one-to-one mapping between the disks of the source VM and what we call recovery disks. But all of those disks during replication are connected to the target VRA. Now, we saw a bunch of disks, a large number of disks. All of the stuff I saw before was for a single protected VM, and we know there are many VMs can be protected to a single target VRA, and there are limits on the number of disks that you can connect to a single virtual machine. That's why we invented those additional VRAs. Many of you that have those larger hosts notice there is a VRA, and there is a number of VRAs that are called VRA-H. Right? All of those additional Zerto VMs that are created on the disks. Now those VMs actually, we like to call them as disk boxes. All they do, those are VMs that have disks connected to them. They don't consume any resources, no memory, no CPU. They just hold the disks, and these disks are used by the VRA to extend, by the sort of the primary VRA, and pretty much extend the disk count, and we get an unlimited number of disks on a single VRA, which enables us to condense and protect a lot of VMs into a single host. Okay, so now let's talk about the journal. Previous slide, I saw that the journal is a number of disks, one or more disks connected to the VRA or to the disk box. And what the journal provides, what do we want from the journal? Okay, the system wants from the journal, the system needs queues. It's all about queues. And we call them, we refer to them as the FIFO queues, first in, first out. And the way it works, we take a number of virtual disks. Each one of these disks is actually chunked up into 16 megabyte chunks. And then the system takes a number of chunks that do not need to be consecutive, linked them up as a linked list, and uses them as a queue that I'll later explain, which is the basis for the journaling algorithms. Okay? But then it's very easy to grow those queues. You just add more grains. We refer to the 16 megabyte chunks as grains. You add more grains to the list. So you get a larger queue. You take array and add them to the free pool, and you shrink the journal. Okay? Now, the sizes of the disks and the number of the disks can change dynamically, and in many cases do change dynamically. Because when we get a large number, when we utilize all of our grains, we will either increase the size of one of the disks and then get more grains into the pool, or in some cases, we will actually add more disks, again, chunk them up into 16 megabyte grains, and again, get a lot of new grains into the pool that can be used for the FIFO queues, and the other way around. Once they empty up, we can defragment it, start moving all of the used ones into one journal disk or less journal disks, and the ones that are completely free can be released, and storage can be and we can release the storage. Okay? So what does this give us? I haven't even started to discuss how it's used for replication, but this gives the system a mechanism to allocate first in, first out queues, a number of them, a dynamic number of them, grow them, shrink them, grow the storage usage, shrink the storage usage according to what the replication system needs. Okay, and needless to say, all of that is managed within the VRA, within the virtual replication appliance. Okay, now basic data flow. Like I said, there is source VM. Does this work? Yes. Source VM, writing data to a source disk. Source VRA captures the data, sends it over to the target VRA. Now the journaling starts. Every protected disk, not protected VM, is allocated a queue, a first in, first out queue. We like to call it the primary queue from that journal. As I said in the beginning, there is one journal per VM. That journal services multiple protected disks, but each protected disk, and we're talking about the virtual disk, obviously, gets a FIFO queue, a dynamically growing and shrinking queue. The data is written by the VRA to one side of the queue, and at some point in time, taken out of the queue and written to what we call the recovery disk. Now, what does that mean? That means that the recovery disk is actually an image of the protected disk from some time ago. Okay? Let's say the journal was configured for a week. Then what you would see in the recovery disk is actually what the protected disk looked like a week ago. All of the IOs that were performed during the last week are queued up in the journal, in the queue. Now, when something grows older than a week, in my example, the configured history time, it is what we like to call applied. It is removed from the queue and written to the appropriate location in the recovery disk. This makes sure that the recovery disk doesn't get too old, and it also makes sure that the journal doesn't grow, because we took it out. We shrinked it from the other end. So what's the size of the queue? The size of the queue is exactly all of the IOs that were performed in the history that was configured by the user. Okay, and in the previous slide I explained how the fact that the system decides what size of queue it needs, the underlying infrastructure can grow and shrink it and utilize storage accordingly. Okay, so I'm going to move to failover. Before I move to failover, any questions on this? Yes?
The helper VRAs.
Yes.
Do you need a networking component?
No. So the helper VRAs are not, so the question was, do the helper VRAs need networking component or need to be configured? They are not configured to anything. They are not connected to network. They are not really running an OS. Okay, they have a very small boot sequence, which is, I'm embarrassed to call it an Opera OS, but it's an OS that we wrote that simply does nothing and does not consume resources. It's just there to hold disks. That's why we like to refer to it internally as a disk box.
So how does the VRA process the information of the disks that are attached to the helper?
Okay, that's done from, that's a good question. So how does the VRA access? So VRA accesses its own disks, but how does it write to those other disks? And that's done through the driver. Okay, it's done through the same mechanism that is able to filter out and listen to the IOs that the production VM writes to. Okay, so that same mechanism also enables the VRA to access those disks that are connected to the helper VMs. Okay, so this is what it looks like normally, right? Journal is growing, shrinking, IOs flowing through the journal. But how do we use it for failover?
Sorry, can I ask a question?
Yeah.
Journal?
I think you could just
Yeah.
With the journal, you said it grows and shrinks,
Yep.
but you're setting a hard journal limit and you're setting a hard time for how long you want it to be. We've seen, if you don't say you're setting it for a week, you might have, if it's a small IO, you might have more than a week's worth of checkpoints in that journal. So how is it growing and shrinking if it's going to use, it looks like it uses the time.
Okay, so let me explain. The primary way to configure the journal, so the question is, are there, if I have to rephrase the question, are there and what are the scenarios where the journal will contain more data or less data than what was written, than the configured history? Okay, is that the right way to phrase it? Okay, so like I said, when everything works perfectly, you configure the time and you don't have to worry about anything else. But there are cases where we need to grow the journal and we can't. Why can't we grow the journal? Either the user set a hard limit. The user said, well, I don't want you to fill up my data store, so don't pass the 100 gigabytes or whatever I configured. But then if we reach 100 gigabytes, we're not going to grow it. And then you will get an alert that you're not meeting your history SLA. Right? You asked for a week, we're only giving you 3 days, but that's because we hit the journal hard limit. Now, just like the journal hard limit, we can also hit the data store limit if the data store doesn't have capacity. So that's on the maximum side. Now, the journal also has a minimum. It's very small. Think a few tens megabytes, I think, right? It's very small. I think it's a couple of grains, 32 megabytes. And that's the minimum. But if your application is not generating any I/O or very little I/O, then 32 megabytes might be enough. You configure a week, but it might be enough for a couple of months. Right? These are the edge cases. Then you will see the journal providing you with more time than you configured.
Okay, and if you fill the journal up and it's then going to dump to the recovery disk,
Yeah.
how much does it dump? Just enough set amount, set percentage or whatever of the journal?
So the journal dumps all the time, just enough, right? Just enough to keep that I/O. So that last I/O, if you configure the week, this I/O is just a few seconds off the week old. And when it gets too old, it will be dumped. That works all the time. That works continuously.
Okay, so, but if it reaches the max size before
Oh.
the time,
If it reaches the max size, then again, it simply won't grow, right? It will take out a little bits and pieces of it in order to let you write in more. Just enough for the next I/O to get in the queue, so you won't have, so it won't grow too large. Yes.
So then, is there a risk, let's say you've got a large file server and you get hit with ransomware and it starts encrypting everything and your change rate goes crazy. Is there a risk of those changes pushing you out of, like, so it has to start flushing the older ones to make space for all these new changes. Is there a risk of overrunning that? And not having enough journal to go back to before when it started encrypting?
So in theory, yes, but obviously if you have enough space, we're not recommending to put the hard limit just a little bit more than you want, right? Hard limits should be hard limits. So what we would expect in this case is you should have the best practice would be to just let the system do its work, because if you do have enough journal, then it will save you from the ransomware. But you're right. This level of the system does not know that the I/Os coming in are not important, they are bad. Okay? So let's move on. Now, let's start thinking about how do we fail over? How do we provide images from this? Okay, so we have these I/Os. By the way, we have the checkpoints. Checkpoints are sort of like dummy I/Os without data. They're created by the source side on a very granular basis, seconds apart. I'm not going to discuss the checkpoint mechanism. That's a whole different presentation. But those get into the queue, just like the I/Os. Okay? If we look at the example, we see those I/Os, right? And the checkpoints in intervals. In the example here, it's hours, but it should be seconds, right? Seconds apart. Okay? And in theory, the way to get to an image is just to apply to a certain point in time, just to apply all the way through to that checkpoint, right? This for checkpoint or whatever, right? This would enable us to get to a point in time, but that's not really how it works. Why? That would be correct. Why? That could work. That could bring us a perfectly good image, but it has two problems. First of all, in the failover event, it writes some I/Os that it doesn't really need. I/Os that are going to be rewritten. And on the other hand, it's not undoable. And as we all know, or most of us that have worked with the system know, that we have a failover test. Means you failover test and then you stop the test and everything goes back to normal. But even a regular failover, and I'll talk about that, is just like a test. It starts with a test. Okay? So what the system actually does, it creates something called a region locator. A region locator is like a map. And the map says for each block in that point in time, the user says, I want to do a failover to a specific point in time. It will say exactly for each block where to find it. Now, some blocks may be located in the recovery disks because they were applied, and some blocks can be located somewhere in the journal. Okay? And that enables us to get an image without rolling forward the entire journal. Okay? I'll explain a little bit further. So what happened in the failover test? User decides, I want to test, selects a VPG, selects a checkpoint, right? Presses go. What the system does, first of all, it calculates the region locator. Okay, it goes over the metadata in the journal and says, oh, like I said, I have a mapping, which block, where can I find it? Okay, now, not writing anything to the recovery disk, not touching the recovery disk, but, well, actually touching it, but not changing its data. The recovery disks are actually detached from the VRA and connected to the newly created test virtual machine. Now, the journaling continues. Everything continues as normal, but whenever something changes, whenever a block is applied, the region locator is updated. So the VRA always knows where to find every block. Now, let's say now, like I said, we didn't change anything, and the recovery disk that's connected to the test VM is a week old, but the checkpoint that I selected was an hour ago. So how does that work? Now let's see, the test VM, let's say it tries to read a block. That read is actually handled by the VRA, and the VRA says, oh, the VM is trying to read block 50 or 1500. Okay, let's look it up in the region locator. Oh, it actually resides in the journal in that location. So it services the read by actually providing the data from the journal based on the region locator. But what happens if the test VM writes data? So for that, when you do a failover test, we create a scratch area, a scratch disk. Okay, I think Iceberg mentioned it today, that we want to monitor those scratch disks, that they don't fill up, or don't fill up our data stores when we do those long failover tests. That's a scratch disk. Now, what is a scratch disk? It's really another addition to the journal, but a dynamic one. It's on its own disk because we're going to throw it away when we're done with the test. So that, again, for my example, test VM writes an I/O. The I/O is simply stored in the scratch disk, and the region locator is updated. So next time it reads from the same block, the VRA knows, okay, I'll get it from the scratch. Okay? So all of this time, the recovery disk has not changed a bit. It is actually still going on as part of the replication. When we stop the test, very easy. Take the recovery disk, connect it back to the VRA, throw away the scratch disk, throw away the test VM, and you're done. Nothing, no impact on replication. Yes?
During live failovers or moves before commits, is the data written to the scratch disk and then the scratch disk written to the actual disk once committed?
The answer is yes, and that's exactly the next slide. Okay? So that I said failover test. Okay, so what I like, so in this presentation is to ask, okay, we have one live failover and move. What's the difference? Because we force the user to do a test before the failover, before the move. You can't go straight through. Well, you can if you just auto-commit, but you shouldn't. Okay? You should test it before you commit it. Okay? So, what are the differences? Not that many differences. Okay? So at some point I asked this question, and one of the answers I got is that the failover test before failover can be committed, and a failover test cannot be committed. Okay, so that's an answer. That's not what I meant. It's mainly around networking. Okay, so a legitimate question would be, why do we have two buttons, a test and a failover? And the answer is networking. Because when you failover test, you want to bring the VM typically in a sandbox, in an isolated environment. And when you do failover live, even when you're just testing pre-commit, you already want to do it in the production network. And we don't want you to have to change the network when you commit. because you tested everything, you don't want to break everything after you've already tested it, okay? But other than that, technically, under the hood in the VRA, very similar. But then, at the end of the failover or move, of the live failover or the move, you've got the commit, okay? And what the commit does, it takes all the data, so we have the region locator. The region locator tells us some of the blocks for our image are already on the recovery disk. Great, they're in the right place. But other blocks are either in the journal or in the scratch disk. So what the system does, it lets the user keep going, right, just like the test, but it forces all of it, goes through the region locators, goes through all of those blocks that are in either the scratch disk or the journal, and copies them over to the recovery disk. That's what we call the promotion process. Okay, everybody here that has done a live failover or move saw that everything was going on, you're already running the production, but there is another progress bar that could take, I don't know, minutes, maybe a few hours. That's called the promotion process. Okay, it's out of band, but what it does, it actually copies everything, and when it's done, you're done. When it's done, it's just a regular VM with regular disks, and you're done with the failover or move. Okay.
Quick question.
Yes.
So while you're running a test, the journal does not drain, is that correct? You've got the recovery disk attached to the test VM, so the journal just continues to fill and fill, nothing comes out.
So the question was, let me if I rephrase the question, do we apply out of the journal during a test? And the answer is yes. We keep applying. All we have to do when we take a block out of the journal into the recovery disk, we just need to make sure that the region locator is updated and knows that to look for it next time in the recovery disk. Okay? Again, until you reach that checkpoint, the checkpoint that you selected for the test, you cannot apply that one. If you get to that, the journal will stop applying and will start going. Okay, so let's start moving. So we talked about journal, talked about entity, we talked about how we use it for failover and test. Now another application for the journal is to synchronize the source and target without taking snapshots. Okay, if you think about it, it's very easy to synchronize two disks that does not change. If it does not change, synchronization is the easiest process in the world. You copy it. But if it changes, it's difficult, okay? So the classic way to do it is to take a snapshot. Snapshot does not change, and to copy from the snapshot. But we in Zerto do not like snapshots. So we're using the journal, okay? And I'll explain how it's used. First of all, what types of synchronization do we have? We have what we call an initial sync, a delta sync, and a bitmap sync. And the only differences between them, they all work the same, except the differences are which blocks do you sync, right? In initial sync and delta sync, you would sync the entire disk. In a bitmap sync, you would only sync those blocks that the system knows might have been different. And the other question is, do we have a delta to compare to? Do we have some kind of preseed on the recovery side? Initial sync is done once at the beginning when there is nothing on the recovery side. So we have to send everything over the WAN. But if you have to do a sync again, either delta or bitmap, you can always compare the checksums between the blocks, even blocks that you don't know whether they're different or not. You can compare them, and then if they're the same, you save on the bandwidth. Okay? But other than that, they work exactly the same. And I'll explain how. Okay? So, first thing we do, we have large disks, right? And truth be told, when we started Zerto, we were scratching our heads. How do we do this synchronization? And we found an algorithm that works well, but only for very small disks. And it works well, but it's limited. So how do we do it? We separate the disk into three areas. One, the first area on the left there, the gray area, is this part that's already in sync. the middle, the yellow one, is the one that's in progress, and the white one is the stuff that we haven't gotten to yet. And if you think about it, that already solves the problem, assuming we know how to synchronize small disks. Why? Because for the synced area, what do? We just replicate normally. Every I/O coming in, we will replicate it. Right? It's just like a different disk that's already in sync. Great. For the white area, what do when an I/O comes in? Nothing. We don't care about it. It's later. We'll get to it later. And the yellow area is the area that we're syncing right now, but that's a small area. And I already said we know how to sync a small disk. Okay? So great, that solves the problem. So how do we sync a small disk? Only the yellow area. What we do, we start copying out. First of all, we put everything in, when I say copy, is reading from the source, putting it in the journal, not on the recovery disk. Okay? Putting IOs, we call them sync IOs, because it's not an IO that the system generated, it's an IO that's generated by us by reading data. Okay? We put it in the journal, in the FIFO, in the queue. Right? But then all of the new IOs that the source VM has been writing throughout the time, they are also written to a queue, a different queue. And as I said in the beginning, we have a mechanism that can generate for us as many queues as we want. Okay, that's what we call the sync queue, obviously. And then at the end, we merge them. What does it mean to merge? These are linked lists. We just put all of the new IOs behind, that's a very important point, behind those sync IOs, those IOs that we generated. Now, for an IO, if you're an IO in the journal, you want to be in the back of the journal. Why? Because the IO in the back of the journal is going to overwrite. It's newer. The newer IOs are always in the back. Okay? And we always assume that the IO that the virtual machine wrote is newer than whatever we read from the disk. Okay? And then we put everything. Everything here is already in the journal. And it's going to be applied normally, like IOs that in the normal replication flow that I described in the beginning. Okay? So that's how it works. That's a little bit more complex. That's how it works for that small area in the middle. And why does it work only for a small area? Because we don't want that merge queue to get too large. Okay? So, but as long as it's small, then it's not large. And it works, and it's consistent, and it's without snapshots. Excuse me. So, any questions on that before we move to the public cloud?
So let's say you've got a VM and a VPG, and I'll take an example that I saw. So my application team was updating a piece of software. They went ahead and snapshotted it in vSphere. Something failed on that, and they actually had to roll back to the previous snapshot. And then when we tried to fail it over, we noticed that the machine had failed, and we wound up having to do a force sync. Is this something that can actively be looked for within Zerto going forward?
Yes. So the question is, what happens when the source disk is changed underneath the Zerto system? And in this case, what caused that change is a rollback from a snapshot on the production side. Okay, it could be a vSphere snapshot, it could be a storage snapshot. Now, in this case, what needs to be done, and again, this presentation, I'm focusing on the data path component, on the really, really low level. What you need to do in this case is trigger a delta sync. Why? Because the system does not know what blocks that underlying change, what blocks it changed. It could be that it didn't change anything. It could be that it changed everything. So the right thing to do is a delta sync. How do you trigger a delta sync? The manual way to trigger a delta sync is a force sync. Now, we are, and I think it was even implemented at the management level, but I'm not sure. But in any case, that's on the management level to listen for those events in vSphere of a snapshot restore. And if we see that if the ZVM, which is a component, a management component, outside the VRA, obviously, when it notices this event, it can trigger that for-sync automatically. Okay, that can be done by the ZVM. That can be done also, can be scripted external to the system, right? Listen to the events in vSphere and for-sync in case it happens. Any other questions at this point? Okay. So I explained how it works in a vSphere environment or Hyper-V. Hyper-V works exactly like vSphere in a hypervisor environment. But then how does it work how does all of this work in the public cloud? So we start with Azure. And from an algorithm perspective, it's very similar. You've got those same entities, those same logical entities of a journal and a recovery disk, but we're actually utilizing what the infrastructure gives us. So the journal uses block blobs. Block blobs, for those who know, that's the object storage that the Azure infrastructure provides. And since this is actually a queue that is written once and then deleted, it works perfectly with block blobs. Because whenever we want to put something in the queue, we just aggregate them up to a certain size, let's say a megabyte, I think it's a megabyte chunk, and write them up as an object. And when we need to apply, we will read that first one in the list, and apply it and delete it. Okay? Now, the advantage of this is that there's no sizing. Well, there is some sizing. Everybody here that has worked with public cloud knows that that infinite capacity is in theory, not really in practice, but much less sizing effort. Right? You don't have to worry that much about data stores and sizing. It will grow and shrink and simply take more capacity or less capacity. Now, what do we do for that recovery disk? We use page blobs. Page blobs are very much like disks. Those are storage blobs in Azure that are read-write. You can change them. And you can actually connect them later on to a virtual machine as a disk, very similar to a VMDK file in VMware. Okay? So, but other than that, very similar, again, at the algorithm level. Next one, AWS. AWS does not have a page blob equivalent. AWS has S3, which is object storage, like block blobs in Azure. And the disks that are connected to VMs are actually in EBS. That's a different storage, and EBS disks cannot be written to from an external machine. They can only be written to, they can only be accessed by the virtual machine that owns them. So, in AWS, all the replication goes to S3. Journal, just like Azure. Written to the end, removed from the front. For the recovery disk, and now I have to put in quotes recovery disk because this is nothing like a disk. We take that recovery, what we refer to as a logical recovery disk, we split it up into smaller chunks, and each one of them is an object, and every time we apply, we will actually replace the relevant objects. Okay? And that's why in AWS you would see the apply not occurring continuously. Right? You asked me if this happens continuously. In VMware, yes. In Azure, yes. In AWS, no. Why? Because we want to aggregate a lot of IOs, and make as little changes to those recovery blobs as possible, recovery objects as possible. We don't want to replace them too often because you can only replace them in S3. And then when it's time to recover, we take all of this stuff and import it into EBS. Copy it again out to EBS. And that's copied. Initially, it was done by an AWS import functionality. And then we actually invented the scale-out importers, which are worker VMs that are automatically generated by Zerto and do it faster. Any question on anything? Because that's pretty much everything I had.
So I'm assuming it takes a lot longer to recover in AWS than it does in Azure.
That's true. That's absolutely true. The RTO in AWS is longer than Azure because you have to copy, you have to import all the data from S3 into EBS.
So let's say it takes 5 minutes in Azure. How much of a difference is it in AWS?
So it's hard to say because there are different components at play. In AWS, the primary factor would be the size of the VM. The larger the VM, the more time it will take to import. In Azure, the size of the VM doesn't matter. So why does it take time? There are other things that work. There's the promotion process that needs to occur. And there's some management stuff that needs to be done, creation of VMs, there's some overhead, which is unrelated to anything. So there are different factors at play. But for larger VMs, you would see in AWS a much higher RTO than in Azure.
You mentioned minimum size of grains. So there's a maximum size of a collection of grains as well? Would that relate to a maximum suggested journal size? Is there a...
do we have a maximum journal size? Not that I know of. We've not seen a data store. Keep in mind the journal doesn't grow that large. In order to get a large journal, you need to generate a lot of IOs.
Sure.
I don't know of any such number. I'm sure that in theory there's always such a number, but we were able to, so data stores typically fill up much faster than we would get to that limit. It does not consume memory. For example, there's no memory impact of the journal there's nothing that is linear between size of the journal and memory that is used in a VRA. Okay, so it's just disk. No number I can provide there.
Okay, thank you.
Since the grains are 16 meg, but you may have, for instance, on the host on a database, 4K writes. How does the block size for writes on the host relate to the grain size? Is there, for instance, write amplification of using a lot more storage for that?
So the grains, the size of the I/O doesn't really matter to the size of the grains because as far as the replication application is concerned, it has just a stream and a huge stream of data. And that stream simply puts the IOs one after another. It doesn't matter if it's comprised of a lot of small IOs or smaller number of large IOs. Okay? Now, but now you want to write to the journal, I don't know, 100 megabytes of data or 200 megabytes of data. So you will write them up into those 16 megabyte chunks. So the size of the IOs that are written to the journal is unrelated to what the application does. The application can write, regardless of your application, and that's actually an important point, the IO pattern that you will see on the journal will always be consecutive 16 megabyte writes. You will never, it doesn't matter if your application is running small IOs, or small random IOs, or large consecutive IOs. Okay?
So is there a good way to calculate your journal size? What it's going to be for VPG?
So we do have some calculators, and we are so we have manual calculators that are available today. We have the Z planner that was announced by Rob. Will also assist in what you need there. Okay, and this way you can estimate what the journal will be once you configure the VPG. And again, another way to do it is just try it out. You can set a smaller limit and see how much history you get, and then decide whether you want more or less. But again, in many cases, especially in larger environments, there's a more detailed planning stage, and that's exactly what the Z planner is used for. And before the Z planner, there was a sizing tool based on Excel that customers typically used. Okay, I think we're done. Okay.
I think that's it. Any more questions?
Okay. Thank you very much.